Artificial intelligence, or AI, is an area of computer science that emphasizes the creation of intelligent machines that work and react like humans. We are now surrounded by machine intelligence. These technologies are fundamentally gonna change our society. But the pattern here is that AI might take a little while to wrap its tentacles around new skills, but when it does, it's unstoppable. We are rapidly headed towards digital superintelligence that are far exceeded any humans. People say it's the future, but really it's not, it's the present. How could a smarter machine not be a better machine? However, the number of road traffic deaths continues to increase. Million people die every year. And that's what are we trying to solve. The main reason of driver distraction system is to make sure that the driver's eye is focused on the road. To detect this, we start by using the head pose model that gets the driver's face angles in 3D space. We used this deep head pose model because it's one of the best performing models for head pose and angle estimating for 2D images. And it's an end-to-end approach, so there is no need for intermediate feature extraction, like facial landmarks and so on. Let's talk about the pipeline. A camera that is set in front of the driver that takes a frame every very small interval of time. Then we take this frame as an input for the model to extract this face position. Then we forward the part of the frame that has the driver's face to the head pose model, which processes it to an output, the driver's face angles in 3D. We use these angles in ranges to determine if the driver is focused on the road or not. The intuition behind the technical part, the network is consisted of a feature extractor that extracted the feature of the face from image, like the position of the eye, mouse, and so on. The feature extractor is consisted of resonant architecture. This architecture is based on convolutional neural network, CNN, that is very powerful for feature latent extraction and spatial information in images. Then these features are entered into 3 different fully connected layers. So each layer predicts different angle in a specific direction and range. Each fully connected layer predicts 2 values. First, the range of the angle could be, and the prediction of the value that angle it can be in 3 to 6 degree region, so we can obtain the exact angle. This approach is better than predicting the angle directly, as this approach uses the most stable classification prediction to pick the angle range, then predict the angle in a smaller range. And also, in the training, it backpropagated through the 2 different losses, classification and recent losses, which means more training.
One of the many reasons to get distracted when the driver is using his hands and drinking or using the phone. So, by classifying his actions, whether he is sleeping, talking, or even drive safely, we can minimize car accidents. Our approach based on driver distraction state farm dataset, which gathers driver different actions into 10 classes, like safe driving, texting using left hand, drinking, fixing hair and makeup, etc. Then specify this problem as classification problem using these classes. A camera will be set on the other side of the driver, and in a specific interval of time an image will be taken to the driver and will be fed to the model to specify the driver action. The model will output probability to each action. The highest probability will define the driver action. If the driver is not safely driving for a consecutive sequence of frames, we will classify him as distracted, and based on the specific action, we will take an appropriate response to guarantee the safety of the driver. As we have a small dataset, we needed to use augmentation. by defecting the photos using color manipulation, rotation, resizing, and cropping, which enable us to getting way more unique images using the old ones. Also, we built our model using ResNet architecture because it's the state of art in image classification problems, and by the power of transfer learning, we can utilize a network that was trained using a huge dataset and fine-tuning it using our problem domain dataset. We also froze half of the network layers as they extract latent features to guarantee high performance and faster training. After lots of experiments, we have gotten an accuracy close to 90%.
We want to build a voice command system so the driver won't use hands for the most common car functions. But it's hard to process speech directly to convert it to actions. Instead, we will convert the voice to text using ESR, automatic speech recognition, and then the text will be converted to car functions that are most used, as it's easier and more efficient to process text than voice. We will use DeepSpeech as our ASR as it's open source, so adapting and changing can be made to meet our specific problem. DeepSpeech also provides regular updates, helping community and adaptation to state-of-the-art technologies in ASR. They also provide a trained general ready-to-use model without training, as the model training requires powerful GPUs and much time to train, up to a month, and also it have a huge benefit of running locally without internet. To wake up the voice system, we will use a trigger word like here Cortana and Alexa. Then after waking up the system, the model will listen to the driver command until the driver stops talking. The model converts the voice to text. Also, the model utilizes a language model to fit words together to build a sentence. Then the text will be fed to the next model to manipulate it to car functions. This model architecture converts the voice to spectrogram of frequencies to get the most important frequencies regarding to human voices. Then the spectrogram is divided into parts with a small intervals of time like 20 milliseconds. Then this parts is forwarded to fully connected layers and RNN to predict the character in each time interval. After that, the repeated characters are removed to form a correct word. Then the prediction is forwarded to language model created by us to get the most probable words so the sentence as a whole can make sense. The use of language model will specify the words that are forwarded to the speech model to limit the sentences to be more related to car commands by adapting and training language model with our commands dataset to be specified to our problem.
After taking the commands from the driver and converting driver commands to text, we need to process this text to specify which action to be taken, like adjusting the air conditioning to a specific degree, or check the engine temperature. We had a problem finding a dataset that specified two commands and subcommands in the car. So we had to create our own dataset to match our specific problem, also using data augmentation in an effort to increase the diversity of data available for training. We split up the dataset into two main categories, like air conditioning as the main command, on, off, or a specific degree as a subcommand, or the car state and engine temperature, or even the radio to turn on the radio or change the channel. The text produced from the previous model goes to text classification model to be classified to a specific category, and then we use entity recognition to classify what each word referring to. And based on the category classified, we will search for a specific info that will help us to execute specific action, whether it will be an actual action in the car or notify the driver with some info. This is still a work in progress that will be updated in the future. We are using an edge device so we can run our model locally without needing internet connection. We decided to use just a nano board because it's one of the cheapest boards that has powerful GPU to run our model smoothly. However, the GPU is still less powerful than other GPUs we used to train our models. So We will need to perform some compression algorithms, like quantization and pruning, to make the model smaller and efficient, and still preserving the model accuracy. After doing all of that, we will deploy our models, and it will be tested in a real-life environment. This is the main step after finalizing the models. In conclusion, there are two main parts to the project working in parallel: the monitoring part and voice commands part. The voice commands part will be triggered by a specific word to listen to the driver commands, process these commands, and execute them doing an action, or notifying the driver with some info. The monitoring part will focus on two types of distraction. The first subsystem detects if the driver focuses on the road by watching his poles. The second subsystem will detect if the driver is safe driving or doing an action that impedes him. And based on these info, we will take some actions that will guarantee his safety.